Hello, everyone. Welcome to Foresight's Molecular Machines Group. Today, we're so lucky to have Baihao Shao with us. And this year, he's a Foresight Fellow, and he's recently a professor in the Department of Biomedical Engineering at Chinese University in Hong Kong. So today, he'll be talking about using light to make biomaterials smart. Thank you so much, Baihao, for joining us.
I'm going to share my slides now. All right. Can everyone see my slides okay and hear me well? Good. Okay, great. So thanks, Lydia, for hosting this seminar. It's a real pleasure to be able to present in this Foresight Molecular Machine seminar. So my name is Baihao. So I just recently started my independent career in the Department of Biomedical Engineering at the Chinese University of Hong Kong. So as you know, geographically, I'm currently in Hong Kong. So the time now here is like 1 a.m. in the morning. I didn't realize that to have a meeting with the fellows from the West Coast, the time difference I need to fight against is this huge. So what I would like to share with you today is partly of my PhD work together with my postdoc work, and they are all kind of lies under this topic, using light to make biomaterial or material smart. So to start, I would first like to thank the great people that I had the opportunity to work with during my PhD and my postdoc time. So first is the people from the Stevens Group during my postdoc time. These are the people that have been helping me and contributing to the project I'm going to share with you, and also the fellows from my PhD group. And they also have made a tremendous contribution to the work that I'm going to talk about today. So I think today is almost a perfect time because the Nobel Prize in Chemistry this year was just announced just a few years ago. So big kudos to the MOF community. And I think it's also a great reminder that the field of molecular machines pioneered by the Professors Samaj, Satola, and Fringa, and also other researchers, also earned the recognition from the Nobel Prize community back in 2016. So 2016 is the year I started my PhD and ever since then, I was very much inspired by this idea of designing and synthesizing small molecules that could operate at the molecular level to yield meaningful functions. So compared to molecules, atoms are functionless. But once they got assembled, and they will start to have functions, and of course, depending on how they are assembled. For example, the molecule can be made to have some built-in properties. So here I just call them static properties. So they can be like fluorescent dyes that make the fireflies fluorescent, or like aspirins or some traditional drugs, they were made to have some biomedical effects. And also like caffeines that I probably need even more than I normally do for the moment. But when we talk about molecular machines, we normally talk about molecules that have dynamic or adaptive functions. So basically, these molecules need to adapt to be adaptive. They are able to respond to certain external stimuli and to use dynamic functions. So here's one example that is widely existed in biology, which is a photochemical reaction, which is probably currently happening in your eye. So this is rhodopsin, or in other cases called opsins. So these were structures based on cation structures. So having these alternating double bond structures, and one of the central double bond can undergo cis-to-trans photoisomerization upon light activation. So these molecules, it has the function to convert the light triggers into neural activities to enable us or human beings to basically to see colors. So around the topic of developing molecules having adaptive and dynamic functions. So my primary research has been mainly focused on the following two topics. So the first one is basically using light to switch bond, and the other one is using light to cleave bonds. So during my PhD, I was mainly working with a class of photoswitch called Hydrozone. So here the central double bond that I have highlighted over here, this is a double bond, and it can undergo cis-to-trans isomerization upon light treatment. And during my postdoc, I kind of shifted a little bit photo cage. So unlike a reversible system, so photo cage is a class of molecules that undergoes irreversible photochemical reaction. So upon light treatment, this covalent bond can cleave. And in a way to, let's see, therapeutic cargoes you probably install to the molecule. So starting from my PhD work, it's mainly, as the title suggests, around the hydrogen photo switch. I was dealing with this hydrogen functional group, which has the carbon-nitrogen double bond and have an NH group here. So my PhD work is mainly focusing on the mechanistic understanding of the photo switching properties of this class of photo switches, and in a way to develop a better performing photo switches, and ended up developing them into, like, let's say, functional materials. And we explore the use of these photo switches in drug delivery applications and advanced display as well. And more recently, we building on the Hydrozone photo switch, developed a very efficient anion receptors and use this anion receptor to develop a active transporting system for transporting anions using a YouTube setup. And in the following slide, I'm going just to highlight some of the work from my PhD. And so speaking of hydrozones are relatively easy to make. So most of the hydrozones that we made that I made during my PhD are through these two chemical reactions. One is called imine condensation. So you have a hydrazine and the condensing with a ketone, and you get hydrazone. The other one is called a JK reaction. So you have a you have a diazonium salt and put a reactor with a nuclear file to give you the hydrozones. And most of the hydrozones can be made through these two reactions, and there are some exceptions. For example, when you want to have the electron donating group on this Baru ring, we encounter some synthetic issues. And for that reason, we went to apply this diazo coupling reaction, which is very much inspired by these resonance structures as I showed over here. So between the diazonium and the diazo, there is a resonance structure or resonance between these two structures. And we were inspired by this, and then we kind of swapped the polarity of the red ring and the blue ring. So having the electrophile on the top while using a nucleophile. This could be the Briganer region or a lysine region, which could react to give the targeted hydrogen compound. So the reason why we are trying to make the library of hydrogen compound is we are trying to understand some properties of this system. So for hydrogen photo switch, one property that differentiated from other photo switchable systems is extremely long thermal half-life. So the thermal half-life basically refers to how long does it take for this thermal unstable form relaxed back to the thermal stable form. So for this particular system, the thermal half-life is very long. It can go up to hundreds of years. So after we make a series compound, we basically were successful to identify some exceptions. So mainly referring to those molecules showing, let's say, the decreased thermal half-life. And across a library of around 10 compounds, we identified a few, especially the one when we have electron donating group at the bottom or having electron withdrawing group at the top. We have observed a substantial decrease in the thermal stability, and it is because of the existence of this resonance structure. So having the donating group on the bottom or having a withdrawing group at the top is going to favor this resonance structure. So the molecule can relax back single bond state, which is having a low barrier. And when we are looking more into the, let's say, the crystal structure of the hydrogen, we found these molecules in the crystal structure. It has a relatively untwisted rotary ring. So here is relatively, so this ring is pretty twisted. It's not having much. And then it becomes quite intuitive to us that what if we cyclized it? And then we want to make this molecule, and we found this compound exhibit also decreased the thermal stability. And then we hypothesized this because the ground state depolarization is also going to contribute. So throughout the study, we kind of have one electronic factor and one steric factors to explain why the extremely long thermal half-life was observed in our system. And again, the crystal structure is proving that. And like I mentioned, in the Hydrozone system, the Rotary ring adopts this twisted configuration, and we found that this twisted Rotary ring is very crucial for the solid state that we observed later on. So across all the crystal structures, we basically identified a packing-dependent emission and the switching structure property relationship. So essentially, when you have a very tight packing, we will have a less efficient photo switching in the solid state. And when it starts to get loose, so going from a head-to-tail to an orthogonal configuration, the photo switching is going to be more efficient, and the fluorescence is going to increase in its intensity as well. So one particular molecule that we found that we throughout the structure property analysis is this compound having this dimethylamine functional group on the rotary ring. We found that this functionalization makes the molecule fluorescent, and since it's the photo switch, so we can switch the molecule between two configurations, and we can also switch this emission on and off as well. So with this molecule, and we were able to basically do a real-time laser writing. So this is a solution, a toluene solution of the molecule that I just showed to you. And here we are using a blue laser, which emits 450 nanometers, is the wavelength that's going to be switch the molecule from the fluorescent form to non-fluorescent form. And in this way, we can, in real time, take advantage of that photoisomerization to do the real-time writing. And as mentioned earlier on, this process also occurs or taking place in the solid state. We can do the same thing in the solid film. So for example, this one is like we deposited the molecule onto a plastic film. So how it works is actually you are holding a handheld iPad and using a LED. You can basically draw the patterns similarly, and this whole process is reversible. And by using a photo mask, you can drawing different patterns on that one as well. So now we have a photo switch that comes with a coupled configuration and fluorescent switching properties, and then we use this system and then to develop to incorporate this molecule into a amphiphilic copolymer and developing a polymeric drug delivery system. So this amphiphilic polymer can co-assemble with the doxorubicin to give a nanoparticle, which upon light treatment could expand to release the doxorubicin that's being encapsulated. So with the coupled configuration and the fluorescence switching property, we can first take advantage of the photo switching property to control the morphology of the nanoparticle that we developed, and following the fluorescence coming out from the photo switch, we can follow the cellular uptake of the nanoparticle and follow the nanoparticle expansion process by following the decreased fluorescence of the photo switch. And we also observed the therapeutic effect. So basically using light demonstrate a higher cell toxicity. And following the decreased change in the fluorescence, we can quantify how much drug that's being released. So all these functions are enabled by just one switch. So passive transport and active transport. So the first one, the passive transport, so doesn't require external energy, and it goes down a gradient through diffusion and towards equilibrium. While the active transport is completely different. It requires external energy input and to move against the gradient, and normally through a pumping mechanism and the system, and in a way to push the system out of equilibrium. And this active transport is something that molecular machinists are more interested in. So one of the projects that I've been doing during my PhD So it's on this hypothesis. So looking at the hydrozone structure, the biggest structural transformation or structural change that molecule undergoes during photoisomerization is it goes from a closed six membrane to an open six membrane. So we have going from a hydrogen bonded form to a non-hydrogen bonded form, and there's this polar NH bond that's put to be exposed in one of the open form. So we have this hypothesis whether we can take advantage of the structural transformation to develop a controlled anion receptor. So with that hypothesis, we went to design and synthesize this hydrozone tripod. So essentially having three hydrozones connected together into one molecule. And in one form, when all the NH bonds are hydrogen bonded, it's not going to bond to the anion. But when we switch all the hydrogen to the open form, so this polar NH bond will be exposed, and in a way, it can now bond to the anion. And then we first use the NMR to test this hypothesis, and you can see here, when it's in the open form, it does choose a very strong bonding towards the anions, while in the closed form, we didn't see much bonding happening. And to further quantify the bonding constant from both processes, and we are very surprised to find excited to find that the bonding constant differences in this case can go up to 6 orders of magnitude, and especially in the case of like small hydrogen atoms like chloride, bromine, and iodine. And we further confirmed this bonding using other different experimental methods. So now we have a very efficient anion transporting anion receptor. So then we basically try to build on the very classic U-tube setup in supramolecular chemistry. So we started with this U-tube. So the idea here, we have like 2 water phases containing potassium chloride of the same concentration. And then these 2 phases are connected through a organic phase that's containing the photo switch that I just described to you. The idea here is to test whether we can use the photo switch we developed to achieve the active transport of the potassium chloride through this organic phase. So we have the animation to give a brief idea of how the system is working. So the animation is simplistic rendering of the process, and what we believe is on one side, so we are populating the closed form, and on the other side, we are populating the open form, and we are using these 2 wavelengths. We are building a concentration gradient across this organic phase, and we believe it is because, in our case, the difference in the anion bonding affinity between the open and the closed form, which is high enough, is sufficient to drive the potassium chloride to be actively transported across this organic phase. And then this is the result we've been observing. So with this setup, we were able to achieve about 8 to 9% transporting or pumping efficiency of the potassium chloride using this setup, which is corresponding to about 4.2 microwatt voltage build-up. So next, I'm going to shift the topic a little bit to biology. So something that I'm getting more interested in during my time doing photo switch research is the idea to control the bioactivity using light. So the concept of this is actually quite straightforward. It's trying to take advantage of the property of light as it being a clean, non-invasive, and of a very high spatial temporal resolution external stimuli to achieve the local activation of the therapeutics, and in a way to enhance the efficacy by bypassing or decrease the side effects of the bioactive therapeutics. So, but one question that people from the field or people outside the field will normally ask is, how are you going to deliver the light? So this physical barrier, so that the light cannot penetrate very well or penetrate very deep into the tissue, is a technical bottleneck. Is currently limiting the use or translating many promising promising photoresponsive therapeutics into the clinic. So during my postdoc, so I joined a bioengineering oriented research group, and I start to basically approach this tissue penetration issue of light from a bioengineering perspective, and trying to combine like engineering approach to better solve this problem. And I also switched from a reversible photo-switchable system to a irreversible one-way photo cage system. The rationale is, so for the controlled release of the therapeutic cargos, like the one-way, normally the process is one way. You use the light to trigger the reaction and release the therapeutics. So the one-way process is probably enough for that type of application. So optogenetics. So optogenetics is essentially the biological version of the photoresponsive therapeutics. So what people are trying to do in this field is trying to use light to control the neural activity, And when the optogenetic practitioners, they are trying to translating these systems into clinical applications or in vivo applications, they have encountered the same issue that light cannot really penetrate well. But the biologists have very quickly decided or realized that they need to work with engineers to solve this problem. And then they've been developing all these type of LED arrays or LED implants or LED needles. So to physically introduce the light deeper to the tissue through engineering approach. And one thing, I think one of the lessons that I've learned throughout all these examples is you can find out the light wavelengths or the light they are using in these applications are just blue light, which I think in the photo switch or the photochemistry community, the blue light is normally regarded as bioincompatible. So more or less inspired or pretty much inspired by this. Then in my postdoc, I was also trying to bring the engineering approach to help solve the tissue penetration of light. So this is one of the devices that I and my colleague in my postdoc group was helping me developing. So it's a LED, it's an insertable micro LED device. So here you can see there's a dot, which basically is this micro LED device, which is quite small. It's less than 1 millimeter in its size, and it could be mounted to the tip of this needle-shaped micro LED device. And the reason why we want a insertable LED device is because when I was thinking about coupling with a LED device with the photoresponsive molecules, I was thinking something straightforward. So I wanted to work it in a plug and play way. So we can easily introduce this device to the tissue and then turn the light on, let it do its job. And once it's finished, we can easily retract it. And this is just a demonstration to show you this is the kind of traditional way how we introduce the light. You can see the light penetration quite, but once you have the aid of this insertability, and the light penetration becomes much enhanced. So the idea is to, again, use the photo cage that I mentioned to you earlier on to develop a photoresponsive drug, which could release the bioactive form of the drug upon light treatment, and couple with a engineered LED device. And we are currently evaluating the in vivo activity of this coupled system in a deep-seated disease model. And this work hopefully will be out like in the next couple of months. So I just briefly mentioned to you that one approach that I applied is basically to combine with an engineered LED light delivering LED device, and the other strategy that I was thinking is to basically develop a system that could work in the parts of the human bodies where the light penetration is not a big issue. And that leads to this slide. So the subcutaneous administration. So if everyone can record the COVID time, so subcutaneous administration is how we receive the COVID vaccine. Subcu admin has a lot of benefits. So it has a very good patient compliance. It can be operated at the point of care, easy to operate, and enables long-term delivery. And since it's very rich in blood capillary, lymphatic capillaries, so the things that you injected there could have the chance to enter the systematic circulation to reach the lesion sites elsewhere. But one thing that is particularly interesting to me is that the physical barrier here you have overcome is just about 2.1 millimeter skin, which and this thickness, even if you don't use, let's see, the IR light or infrared light, you can easily penetrate the light through using green light or yellow light and yellow light. So following this rationale, and for the project I'm sharing with you now, is trying to develop a photoresponsive drug depot. So again, going back to this body photo cage. So the idea here is trying to develop a body photo cage, using a body photo cage to develop a photocleavable cross-linker, and then using that to develop a hydrogel-based drug carrier. So it drug carrier. And then when we apply the light to this system and we could introduce to the photocleavage of the photo cage, and in a way to degrade the molecule and release the therapeutic cargo. So the idea then, so to developing this hydrogel into an injectable formulation where we can easily deposit it to a subcutaneous tissue, and then we can apply the light to achieve the controlled delivery. So in a long run, and such a system could be coupled with a LED device that could be controlled, let's see, by a phone setup, or to have a more programmed and smarter control over the release process. And then for developing this system, and then we choose to work with a hydrogel, choose to work with the stream promoted azido alkyne cycle addition chemistry, and developed a hydrogel system that has the gel self-forming properties. So we developed a formulation which is consisted of a four-arm peg functionalized with the strained alkyne, and having a body photo cage functionalized with azides. And then I will just skip the synthesis procedure. So we made both two components in-house, and we made them both water soluble. So the reason why we want to do that is we want to avoid the use of any organic solvent. So how this formulation is working is basically you prepare both hydrogel precursors in PBS solutions, and then you can take them and mixing them in pure PBS buffer. And after about, depending on the weight percentage of the hydrogel formulation, after about a few minutes, it will gel, and you will end up with the hydrogel, with this orange colored hydrogel. And we screened a bunch of gel formulations, mainly varying its weight percentage, and we finally ended up stick to this formulation, so 4 weight percent. So as it gives a relatively close to body mechanical property, as well as a relatively quick duration time, which is around like six minutes. So as you can see, because the gel doesn't form immediately, it takes a while for the click chemistry to take place to form the hydrogel network. So the gel is fluid enough to be injected through a needle. So here you can see the gel is quite straightforward to be injected through a 21 gauge needle. And speaking of the photo degradability, so the hydrogel I made is probably different from the hydrogels you normally see, which is transparent, colorless, and the hydrogel here is red in its color. And the reason why is because it can absorb the green light and be photoactivated. So we can apply light to it, the green light 530 nanometer light to it, and we want this photocleavable reaction to take place as much as possible. And over time, you can see this gel on the green light irradiation can start to degrade. and in a way, while it's degrading, it's going to disassemble and to release the encapsulated carbon. So I would highlight here, so one benefit of the light-controlled materials compared to other stimuli responsive materials, using light, you can really control the property of the materials in a precise, remote, and non-invasive way. And next, we try to basically encapsulate some cargoes. So in this case, we choose nanoparticles as our cargo. So the idea is to co-encapsulate or co-duration together, to do the duration together with the nanoparticle. So we can mix them all together, and then you can end up with a nanoparticle encapsulated hydrogel system. And we can characterize the gel formation. It doesn't affect the gel formation, and it can also be photodegraded efficiently. And the SEM image also shows you that we can obtain a hydrogel nanoparticle composite structure. And upon applying the light, we can achieve a light-dependent release of the nanoparticle, and with a very minimal dark release of the nanoparticle. So finally, to demonstrate how this formulation would work like in the real world. So we basically choose to demonstrate on a pulsar belly ex vivo model. So starting with the gel mixing, so two solutions mixing they all together and preload to the syringe. And then we can inject it through the syringe, and after that, gel can again continue to gyrate to become more rigid and to be mechanically strong. So through using this loading injection method, we can deposit two hydrogels underneath the pulsar belly, and we can introduce the green light guide on top of one of it. And over time, after 60 minutes, you retrieve the gel. You can clearly see in the subcutaneous environment, even using green light, we can trigger very effective photodegradation of gels to release therapeutic carbon. And why these formulations are important and can be potentially useful in clinic is because currently in clinic, there are still many medicines or medications that requires daily injection or even a few injections every a few hours, like a lot of injectable painkillers. And we believe that a subcutaneously deposable hydrogel system that's light controlled could help to improve the delivery of such medicines. For example, if we can develop a injectable that's going to be stable underneath the skin, let's say for a week, and we can use light to achieve the controlled release over a week time, and we will be able to improve the compliance of these patients and relieve their pain a lot. So I think that's pretty much everything I want to share with you today. And like I just mentioned, I just recently started my independent career in the Chinese University of Hong Kong. So the campus was built on the mountain. And for that, and we are surrounded by mountains as well. So we have a very nice ocean view together with the mountain view as well. And it's well connected to the metro system of Hong Kong. So basically makes it very easy to access other parts in Hong Kong as well. And my group, again, will continue to work on this idea using light to make biomaterials smart. We will basically concentrate on the synthesis of photoresponsive molecules and in a way to combine engineering approaches to better tackle the tissue penetration issue of light, and ultimately to develop the photoresponsive therapeutics that could potentially help us to promote human health. And we currently have a few postdoc and PhD positions available. So if you are interested and you know someone who are interested, so please encourage them to apply. And the last but not least, I would of course like to thank the Foresight Institute for giving me this opportunity, and thank all the supporting staff for helping with all the logistics. And I'm looking forward to meet all the experts, colleagues, fellows from all the sectors. So thank you for staying up late with me today. So I'm happy to take questions.
Thank you so much, Baihao. That was awesome. So we have about 20 minutes for the Q&A. The way that we'll do it, you can either field your question in the chat or you can raise your hand. Micah.
Do you have any data or estimates for how long the hydrogel is stable in living tissue before it degrades naturally?
So for this formulation, so we tested in the post tissue. The post tissue I mentioned because it's not in a perfusion condition. It's stable for more than 3 days.
Okay.
And we also tested in the perfused human skin tissue. And in that case, because the condition is more harsh, the hydrogel degrades, I think, within 2 days. So that's something we need to look into in the future. Something that we need to deal with, the stability of the hydrogel, based on the results we are getting so far.
Great. Tad, go right ahead.
Hi, thank you. Thanks for the talk. It was an interesting mix of the molecular machines part in the beginning and then the potential medical applications later on. So I had basically 2 questions about the animation in the middle of your presentation on the ion transport. You're showing light to switch between open and closed structures and moving the ions from left to right. So the first question is, after the ion was captured in the closed structure, what is it that moves the combined structure from left to right? Is there an external force or is that a diffusion process?
It's a diffusion process, which was aided by stirring it. So we found that stirring is very important for the system to work. I mean, the animation is a simplest rendering of the process. It's just help to understand how this works. But
that's the slide.
It would be too good to be true that this is actual situation. So we have one molecule bound one potassium chloride and transport from one place to another. And what we think it is because we are building a concentration gradient across this organic phase. So on the left-hand side, because we are irradiating with blue light, so we are populating the closed form. On the other side, we're irradiating with UV light, we are populating the open form. So across this organic phase, because we use 2 different wavelengths, we are building a concentration gradient. And I think the key for this, why our system is working, is because we have a system that's the bonding affinity between the bonding and unbonding form. That the difference is very big. It's up to 6 orders of magnitude. I think that's very key to why this system is working.
Yeah, well, it's a really nice illustration of the whole idea of molecular machines and being able to control them, as you say, with 2 different wavelengths of light. It certainly is a nice example. And so my second question, and sort of maybe you addressed this, but I'm not sure, is in the transport that you're showing here, you're building up a high concentration on the right. Right. Is what prevents, or is it just not shown here, of diffusing back from the high concentration on the right going back to on the left? Is it these objects, they cannot go through the solution unless they're bound with this molecule? Is that the key to it?
So the process is reversible if we store the light irradiation. So the system will slowly goes back to the equilibrium state. So we've been monitoring it over 24 hours. And we have the data in the supporting information. I think more than half. So let's say here is 8 to 9%. Over 5% of that build-up gradient was reverted back to the equilibrium state. So if we keep monitoring the process, I think the system, in theory, goes back to the equilibrium state.
Okay, thank you. It's a nice illustration. Thanks.
Thank you very much.
Great. Bill, would you like to go?
Yeah, I guess I still have some questions about the same slide. So you're starting with KCl on the left side at 25.6 millimolar, but you're also showing that you have KCl 25.6 millimolar on the right side.
Yeah.
So how are you detecting? You're looking for You look at an increase in the concentration on the right side.
Yes. So because if let's say we only have KCl on the left-hand side and we don't have KCl on the right side, and that's going to be a passive transport process because we already have a concentration gradient to start with. So in this case, we have the KCl of the same concentration on both sides because we want to start from a state when the concentration gradient is zero.
Got
So
it.
in a way, and then we are using our system, the transporting that we've been detecting is an indication that we are actively transporting anion against a concentration gradient or building up a gradient. So
Yeah.
that's
Okay.
why here, that's why the setup is like that.
And what is the function of the crown ether shown on the left-hand side?
So crown ether bonds to potassium, sodium, and that's basically help the potassium chloride to better dissolve in organic solvent. Because
But then what's being transported is,
yeah,
okay.
but then the cation will just go with the anion. So we are basically transporting an anion, and the crown ether is to help the potassium chloride to better dissolve in organic solvent.
Got it. And last question is the 8.8% represents
Increase in the potassium chloride
concentration
concentration on the right-hand side.
Got it. Thank you very much. Thank you.
Great. Are there any other questions for Baihao? Okay. Well, thank you so much, Baihao, for joining us and for giving this great presentation. One piece of housekeeping before we all leave the call. We are going to be meeting, as always, the first weekend of December in person in San Francisco for Vision Weekend. We're going to get great speakers from every technology track that we support, including molecular machines. So if you are in town in San Francisco or you're not, we would love to have you and meet in person. With that being said, again, thank you so much, Baihao, and thank you all for joining today. So we'll see you next month.